Welcome everyone to the 2024 Photonics Spectra Summit Series. Thank you so much for attending the Laser Materials Processing Summit, and in this session you'll hear from John McCauley, a Senior Business Development Manager for MKS Ophir. John's focus is on automotive and direct energy applications. He's worked with laser marking and engraving systems since 1998, and he's joining us today to discuss laser characteristics that drift and how to manage the changes. If you have any questions or comments, you can type them right into the Summit chat box that is on your screen. And if you missed part of today's session, you can always come back later and watch it on demand. That's all for me. John, we appreciate you taking the time to join us today.
Jacob, thank you so much for that introduction. It's always a pleasure to work with Photonics Media on these very important topics, and very much appreciate the forum and the opportunity to speak to you. This audience does say something about you, that you're taking time out of your busy day to join me on what I hope will be a beneficial webinar for you, and to give you some information that will be useful to you in your role. So let's go ahead and start. MKS Instruments is a global leader in supplying solutions and systems for primarily semiconductor, electronics and packaging, and also specialty industrial. But we pride ourselves on surrounding the workpiece, looking at a process and supplying components to help the customer achieve what they want to do with whatever process. The Ophir product line is part of the Photonics Solutions division within MKS, and we manufacture laser beam power meters, laser beam profilers, and various ways to measure the performance of a laser beam. So as far as what we're going to be talking about today, just as an introduction, to frame the conversation here, the success of any laser system really depends on a laser that performs consistently. So this is especially true with material processing lasers, and there are a couple of different unique challenges that I'm going to talk about. When you look at any laser system, the success of that laser system really depends on the laser system performing consistently over time. Any laser system, because it's made up of physical components and physical matter, it's got the potential of changing, whether those be short-term changes or long-term changes. There's always the potential of the laser system changing over time. With respect to material processing lasers, we have some additional challenges that can cause its performance to drift off the design performance, and specifically two areas. One, we're working with relatively higher power lasers, and number two, oftentimes, or at least sometimes, we're working in relatively harsh or dirty environment. Those two factors can really have adverse effects on the laser system. So that's really kind of what we're going to be focusing in on, if you pardon the pun there, when in this webinar, and is talking about these challenges with the high power industrial lasers. I'm going to make the argument this morning that measuring and analyzing some key performance indicators on your laser system is really quite crucial to ensuring the long-term success of your laser system within these material processing processes. So as far as an agenda today, I want to start off by talking about the simplest way to analyze a laser application. I want to make it as simple for you as possible. I know your time is money, your time is very valuable to you, so I want to make it as simple as possible. Digging deeper into that, there are some key performance indicators to help diagnose laser problems, and we'll certainly talk about those. Because we are a measurements company, Ophir, we want to talk briefly about how these measurements are captured, and you know, a little bit of best practices there. I want to present a couple of different cases where measurements helped solve these problems as well. And at the end, we'll have a little bit of a Q&A. Power density. Power density is really the most basic, the most simple, fundamental way to tie the laser, how the laser is designed with how the laser is performing within a process. It's a really high level expression of the overall laser's performance. So for example, when we're talking about material processing lasers, it's how the laser is applied to the material that's being processed. And it's expressed in this expression, watts per centimeter squared, where the top of the expression is the amount of light, and the bottom of the expression is the beam size that's being applied to the process. So the top of the formula, it's in watts. It stands for watts or some kind of factor of watts, so kilowatts or megawatts. Also, when we're talking about pulsed lasers, it can also be expressed in joules, kilojoules, millijoules, but it's the amount of laser light that's being applied to the process. This is characterized by the measurement of the laser power or the laser energy for pulsed lasers. And then the bottom of the expression is in centimeters squared normally. This represents the beam size that's being applied to the process. So you're taking, in most cases, we're talking about a focused laser that's taking some amount of light, focusing it down to the process to achieve the desired result. The beam size is also known, in the industry as the spot size, the beam waist, the focused spot, and this is really characterized by the measurements within the beam profile measurements. We'll talk a little bit more about that. How does this expression change? So obviously the numerator can change, the denominator can change, but the numerator can change intentionally or unintentionally. If you apply a higher or a different laser power through a program, it's going to change the watts per centimeter squared, the power density at the site. If there's some kind of adverse reaction to something that's going on with the laser system, the laser power can change, usually decrease over time, and that'll change the expression as well. With changes with your spot size, normally in most cases you won't mess too much with the spot size. You'll generally just change the laser power to change the power density being applied to the process. But there are some changes that can add in your laser system which can adversely affect the beam size being applied to the process, and we'll talk further about that here in a second. But you've got, just fundamentally as a laser system, you've got these input parameters that you as a laser user can change. You can change your laser power. With respect to pulse lasers, you can change the laser energy, the pulse frequency, the pulse width, the pulse shape. There are a lot of different parameters that you can change on your laser system that are tied directly to the laser process. So the power density is really how you take these laser process parameters that you program and how you tie them to the process. So is it an intended change through a change in a laser parameter that you make, or is it an unintended change in one of these laser parameters that affect or negatively affect the laser process? So understanding what power density is really key to understanding how to minimize these changes in your laser system. I took some pictures, through my career over the time. Here's some laser optics that have collected debris on them, had some kind of adverse effect on them, like a material failure or something like this. But if you look closely at these pictures, you will see debris that's collected on either an isolation optic or some kind of cover glass or something like that. Now these defects on these optics obviously will translate into some kind of change within the laser system, whether it be an absorption of laser power causing your laser power to decrease and ultimately changing your power density being applied to the process, or it can cause some kind of thermal effect on the laser system through the absorption of the laser light, which changes the property of the optic, causing it to the focused position, the position of the focus spot to change with respect to where it's supposed to be. What laser measurements are meaningful? So we've talked about power density and how laser power is important to measure, how the beam size is important to measure, but there are also some other characteristics of your laser that should be measured as well. Output power or energy at the work site, that's what we've been talking about so far. Output power energy at the work site is really most meaningful because, and I'll make the argument that you can program a laser to output 1.5 watts in this case. You can measure internally to the laser that the laser is outputting 1.5 watts, but ultimately through losses within the laser system, there is at least the potential of 1.47 watts being delivered to the process, some kind of change off of what the laser is programmed to measure. So knowing that that laser power measurement at the work site, both in a short-term measurement, which you can see here at the bottom right, this graph, what the laser is doing once you turn the laser on. Is it stable over these short time? Is it bouncing around? Is it drifting off of what it's supposed to? These measurements are very important. And then there's the beam profile. This is the numerator of that watts per centimeter squared. It's the beam size, the beam shape, the beam geometry, beam ellipticity. Those are all very important characteristics to measure and to understand. And then there's the caustic. This is what the laser is doing at and around the focus spot. So the Rayleigh length, how much usable laser focus is, what kind of length can you count on? There's the divergence angle that's oftentimes important. And then mostly on the front end when developing a laser source or even running in a laser system, customers are oftentimes interested in the M squared of the laser system, or the beam parameter product is oftentimes very interesting. And then there's the dynamic laser spot location. So is the focus spot that you present to the material, is that remaining consistent, or is, because of some thermal effect, is it drifting off of where it's intended to be? So where your intended focus spot size at the material is, where you think it is, if it's drifting, it's going to be increasing at the process. So understanding and knowing how to account for focal drift is very important with respect to the industrial laser. Laser power and energy measurement, you're measuring your laser power or energy at the work site with pulse laser characteristics. There's also the width, the shape, the frequency, but ultimately what you're going to be doing as far as how you approach this is taking some kind of sensor. The sensor is going to be defined by your laser characteristics. So you take your laser characteristics, define a sensor, and then marry it up with some kind of handheld meter or PC interface to take the readings and to present those readings to the user. There are also some integrated solutions that any laser power and energy measurement company will have, but here's a couple that Ophir has. These are all-in-one, very easy to use, integrated into your system, and then you take that measurement, you present it to some kind of graph. You want to see, what that laser measurement is doing short term, long term measurement. I know a lot of customers who will take the laser measurement and record it in their HMI, and then track that over longer periods of time, and that's very important to do as well. Here's a picture that I took within an automotive plant of an integrated system. So you see at the left there, you see the sensor that is permanently mounted. It's permanently got cooling water that's hooked up to it, and this is for the purposes of taking periodic measurements on the laser system, just to make sure that the laser power is performing consistently over time. At the right there is the meter that's encased and protected from the harsh industrial environment. And then there's laser beam profiling measurements. Again, this is your the denominator of the watts per centimeter squared. This is the beam watch system that Ophir makes. It is a device that looks at the laser caustic and analyzes the caustic in real time. And then there's the beam gauge systems that Ophir makes. These are systems that look and take a cross section of the focus spot and present the image of the focus spot to the laser user. Couple of different devices here, but what you're doing is you're measuring the beam size at the work site, the beam shape, ellipticity, the geometry. You're measuring the focus shift. If you do have any focus shift on your laser system, which will change the spot size at the process. And then you're measuring the divergence, the divergence angle, the M squared, the beam parameter product, all your caustic measurements as well. And that's how you achieve that through some of these products. As far as the approach taken with beam profiling, this is oftentimes very intimidating to laser users. It's really not that. It's really should not be that intimidating as long as you are approaching it correctly. But first of all, you want to attenuate the beam. You want to reduce the laser power so that it's at a suitable level to be analyzed. You want to sometimes size the beam. So, if your beam size is too small, you want to use a beam expander. If it's too large, you want to use a beam reducer in this case to present it to the imager. And then you image the beam, oftentimes with a camera or some kind of scanning slip profiler. There's other methods of doing that. And then once you've collected a suitable image, you send it to your analysis software for analysis. So, that's just a very basic overview of how you approach the beam profiling process. Couple of case studies for you to leave you with. Here is a case where this is a pulsed drilling laser, a picture that I took. You see, number one, the beam profiler with the red box around it. This is a beam attenuation system that's connected directly to a camera. So you're reducing the laser power. In this case, you don't have to resize it because the beam size is suitable for the camera. You're imaging with the camera, and then the camera itself is connected via USB to an analysis computer that's connected to it. You see underneath the laser is this power sensor. The power sensor is water cooled. It's collecting 99.9% of the laser light to analyze the laser with respect to power. It's connected to, I think in this case, it's connected to the same PC that reads the power. And then since it is a pulsed laser, this particular customer was interested in capturing image about the pulses themselves. So the fast photodiode that sits off of the laser light will measure the pulse frequency and the pulse shape to give the user an idea and verify what the pulses are doing in that case. Here's another case study of this particular setup was in an automotive lab. The laser system was a 6 kilowatt multi-mode fiber laser connected to a robot arm, and which had a remote welding scan head that was connected to it. It has a 500 millimeter working distance with a 300 micron spot size. The application of this particular laser system was on the fly 4-second aluminum weld. The problem that this customer is seeing was that there was a progressive loss of weld penetration. So what the laser was doing, it was just starting out welding fine, and then towards the end of the weld, it was starting to lose penetration. And they wanted to analyze the beam. What we found with this measurement equipment, it's a 10 kilowatt water-cooled sensor connected to a Starlight meter there. The meter is the Starlight meter there. You've got the sensor that's sitting on the floor in this case, since it is a long focal length lens, and then the beam analyzer is a beam watch in this case, which is a non-contact beam analyzer, which real-time measures focus shift. And then in the end, we were able to verify not only that the laser had focus shift, was exhibiting focus shift because of a faulty optic, we were able to measure how quickly and how far the shift was happening off of focus. There's kind of a just a representation of what the beam was doing. It was coming down, it was focusing into the device, and then diverging past the device into the sensor for the power analysis. So as far as closing thoughts go, just wanted to wrap things up, put a bow on it. The success of any laser system will really largely rely on its consistent performance. And hopefully I made the case to you that today, and I think everybody can agree that to have a successful laser performance, or laser process, it really relies on how consistently that laser is performing. And hopefully you can understand that measurement of its performance is really crucial to ensuring its consistency, not only at that point in time, but also long term when you're looking at the entire life cycle of the laser system. The material processing laser, especially in industrial environments, because of its relatively higher power, because of its relatively harsh environments in some case, these material processing lasers will have its own unique set of challenges in keeping this consistent performance. So it really is very vital. I'll make the case to frequently measure your lasers to ensure that from day to day, month to month, year to year, your laser is performing consistently over time. Keeping the power density in mind is really very vital for the laser operator, for the laser maintenance person to understand as far as how that laser is being applied to the process. So keeping in mind and knowing and visualizing what your laser is doing and how it's behaving is going to be really most helpful to you in setting up and operating the measurement products with minimal damage. And also taking those measurements and tying it to the process. I'll admit there are many different laser characteristics to measure, and at many different times with different methods of measuring these characteristics, but hopefully I was able to demonstrate to you that at a bare minimum, knowing your laser power and knowing your laser spot size at the process and understanding how those tie to the process are really very vital in understanding how your laser is going to be performing over time. So with that, I'll go ahead and wrap up the webinar. I think I'm a couple minutes early, so there is my contact information there. If you want to contact me offline, I'll be happy to help you with whatever application you're trying to work with and selecting your measurement equipment. Otherwise, Jacob, I'll turn it back over to you and just hope that we got some good information in there.
John, thank you so much for joining us to detail laser characteristics that drift. I just want to echo your statement real quick here and encourage everyone, if you haven't already, you can type your questions and comments into the Summit chat box. And do not worry, if you have not been answered yet, you'll be reached via email at a later date. This session is hosted by us at Photonics Media, and we certainly hope you're enjoying the Laser Materials Processing Summit. Thank you all so much for joining us.